Hi everyone, welcome to Skilled Inspirational Academy. I'm Arjun. Today's class is Wireshark training. So this is a demo class for Wireshark, and today we are going to discuss about, deep about what TCP IP about, and we have different parameters to discuss throughput issues and most common issues we face in the internet connection. So before walk you through those things, let me explain what is the use of Wireshark. So we probably seen people, they use Wireshark for capturing the packets, but from my standpoint, 2-3 years back when I saw Wireshark, it's full of packets and it's so confusing in where to start with and what exactly the packets is talking about. So I had hard understanding about this Wireshark. And then I did a lot of readings, and then it is just like a one capsule I'm giving you with all my readings, and put everything in on the table to make it very easy for everyone to understand and follow the Wireshark training. So that's the objective of this class. The main takeaway of this class would be, once you finish this demo session, you would have solid understanding of what is TCP and what exactly what is inside the TCP packet, because we heard of a TCP, but we very few people, they might peel out every TCP flags and TCP parameters. That so many parameters that maybe for few people, so they may not heard about this TCP flags and TCP parameters before. So this particular class, the biggest takeaway is you would get a complete understanding of how TCP IP works with every parameters and why those parameters are used, and in the modern communication, why this TCP is so important for especially for network troubleshooting. Yeah, this is all about the biggest takeaway of this class. So once we finish this class, you will be so confident and you will understand better about TCP IP analysis. I hope everybody will start enjoying this class. So before start with, let me explain a scenario. We usually encounter this issue. Networking is the one common backbone where all the teams, they keep barking about this problem. They always complain, the networking team, for this any kind of performance issue. It can be a application issue as well. So people might have come from a different background, and I want to give you an overview of OSI model. So we all know the OSI model. It got 7 layers. So the core layer, what we are going to look at here is transport layer. So here works this TCP and UDP. And we all know about that. And we say TCP is TCP is connection oriented. And this is very reliable protocol. Why is that? What is the mechanism that's outstanding when compared to UDP? Why TCP is so reliable? Why people call it as so reliable connection? What is the meaning of it? So when there is a problem, generally what the network engineers, they have the maximum possibility to look around for an issue. What is the cause of an issue? How do they start with, and how they come to a conclusion that, okay, this particular problem is not with the network, it is a problem with the application. So to get a complete insight about a problem, I don't think with the router CLIs and firewalls, we would see the TCP SYNAC. That's a stateful device, right? So it maintains a TCP session. That's for sure. Firewall is capable of it. But to peel out what is inside every TCP parameter, so here comes the Wireshark. So you cannot do that. So in the firewall, to the maximum, what you can do is, okay, if a connection is established between your source to destination, so you can say it is a TCP or UDP. And firewall will give you more control of, okay, this is a stateful connection. And you can see the TCP connection establishment. We call this as a TCP SYN and TCP SYNAC, right? Once these two connection established, then we can say, okay, this is an established TCP connection. So this is a maximum, control we have with firewall. But with the help of Wireshark, what we can do is, okay, what is inside the TCP packet? So it is something like you peel out every parameter in the TCP and you will see what exactly happened. If there is a slowness issue, there can be a multiple problems, right? So, but to figure out all that, the primary is very key thing here. So you cannot just blame it is because of an application. So to prove that, you have to do some basic checks, as you have to, example, you got your head-end router or your core router, customer edge router here, and you have a BGP peering with your provider edge, and you got your core switch. Very simple design here. So we got a couple of PCs connected. And when the traffic is initiated from the client, so you have to check here, right? Even though your bandwidth is too good, you got your 100 Mbps link, it's a fat pipe, and you got, a good bandwidth connection that's in your office, but still people are complaining about the slowness issue. So you can check the utilization. There are many monitoring tools to do that. So one we use is SolarWinds, where we can find the utilization of a particular link. So you can see this internet link is choked, and how to find all that, right? So to prevent this, in most of the enterprise design, what they do, they use QoS techniques. So we'll see where exactly the QoS marking happens and how we can find out in Wireshark. But I'm just giving an overview about QoS. QoS is quality of service. That is something like you are prioritizing your traffic. So maybe few people, they may heard of this, but again, the quick overview is inside the IP header, you can do a marking. That is something called as IP precedence value. That is, you are prioritizing the traffic. That's the main objective. So you are marking your traffic. So if from the switch level, if you do QoS, that should be visible under the layer 2. So what is the quality of service you are using and how you are prioritizing your traffic? Example, you are prioritizing your traffic, something like this. You're prioritizing your voice, and you are prioritizing your data traffic. This is just an overview. This is not much with networking. We'll look deeper inside the Wireshark. So I want to give a glimpse about all this. So I'll mark the packets and I'll give a priority for it. For example, for priority, I'm giving a priority 10, and for data, I'm giving priority 5, because voice traffic is very crucial and it is vital for the network. So people should not be disconnected when they are on phones, when they are using their Teams. So the priority is higher for voice. So you can peel out all your QoS information inside the Wireshark, and you can see, even though if you applied a specific policy to this switch, this L2 switch, but still, if you can see from the Wireshark, if you take a capture from your PC, and if you do a packet for capture from the switch, and if you offload all your traffic back to the client PC, you will come to know whether the traffic is actually, all your packets are being marked with your QoS marking. That's exactly configured on your switch, that's been applied to the specific interface. So you'll get all that kind of deep insights about that using the Wireshark. Okay, that's fine. So now I did my basic checks, something like I checked my internet link and the utilization levels, right? It can be either from your switch, or it can be from your WAN. That is the only possibility, right? So if you got your router, something like this, and it is connected to a switch, and you got your PCs connected here, so it could be either this end or this end or this end, right? So because this is connected to ISP, you'll check all these 3 ends, and you'll look for interface errors, utilization levels, right? If there is any errors, there's something like a physical issue, you will see the CRC errors keep increasing. And if you see any kind of utilization here, it's your bandwidth is choking for 75%. You'll get to know about all this with your monitoring tool. That's fine. So I have checked everything. Now the scenario is I have checked every single possibilities what I have, but I couldn't figure out where the problem is. So now I am concluded that, okay, all this below 3 layers, my physical layer is good, my data link layer is good, my switches actually forwarding all the frames. That's no problem with the switches. And my network layer is also clean. The utilization is quite normal, and there is no CPU utilization on my router or no CPU utilization on my switch as well as my PCs, right? So all the basic checks you have to do. That is very important because network is just like an highway. So if there is a congestion here, then apparently your application will be dropped. Agree? So that's how it works. So my highway is clean, my cabling is fine, my switch is fine, my router is fine, utilization is fine. There is no problem from the network perspective at all. But how do you say, or how do you convince? I would say it is a convincing. How do you prove exactly that, okay, this is not my networking issue? That's a problem, right? Because people, they say, okay, for all good, then why still my connection is bad? Why I'm dropping my packets? Why the communication is not so healthy and faster? So it's pretty slow. So this all the application slowness, generally the people, they complain about this. So how do I overcome this problem? To know about that, I have to give an overview again about the TCP. So it is not that if I send a packet from one source to destination, I'm not pushing the packets without any mechanism. So how I know, how I can guarantee all the packets has been delivered to the destination? How I can be confident enough for about this packet delivery process? So to rule out this issue, they have a protocol called TCP. That is called Transmission Control Protocol, we say. But what exactly it does? So for every packet, it has its own database. Something like it make note of every packet that it sends. So how this mechanism exactly works? Yeah, this is how the TCP parameters helps us. So if I got a big data, so one big data example, it is a 64 bytes data, but I cannot send us a one single packet. So I'm going to chunk this packet into small sizes. So for every packet, I'm going to identify every packet using the sequence number. Why it is used, I'll show you there, but I'll give you again an overview about that. So sequence number. With the help of sequence number, I can track every single packet that's been sent from my source. Example, this is a sequence number 1, and I'm going to send the second packet here. So my second packet is something like the sequence number 2. Just for the demonstration purpose, the real sequence number is different. So this is the sequence number. And before that, actually, if you do a capture using the Wireshark and any analyzing tool, but one key thing you should understand about this Wireshark will use a sequence number called as relative sequence number. Why this is used? Relative sequence number is for the administration is very simple. Example, if you use your raw sequence number, it's very hard to follow the packets. But if you use a relative sequence number, that is something it gives more control. You can actually track down that something starts similar to 211 and it's an increment of 1, 213, 214, 215, something like that. So it is a sequential approach. It gives more control to track down your packets, how many packets has been sent and received. The raw sequence number, I mean, it's again a very big challenge for us to track the packet. So to make it simpler and for the tracking purpose, they have introduced the relative sequence number option in the Wireshark, where if you want, you can enable it. And I would hardly suggest you to always keep it enabling the relative sequence number. So Wireshark displays a relative sequence number by default. In reality, the initial sequence number is 0, and it can be anything between 0 to this many values. It's 2 to the power of 32. That is the maximum value that it can use. So if you want, you can disable the sequence number. If you see an option here, there is a relative sequence number that's enabled by default. I hardly suggest, and everybody, they use this by default. So this is the use of relative sequence number in Wireshark. So coming back to this TCP process. So this is a quick overview about the sequence number and acknowledgement number. And when we talk about TCP, TCP is a 3-tuple connection. It's a three. Sorry for that. Let me write a little bigger here. We call this as a 3-tuple connection. Why it is called as a 3-tuple connection? So to do that, let me open up my whiteboard. Okay, so if this is example, this is a source. And this is the destination. So this is my PC here. And this is my server. It can be not my server, it can be a public server. And I'm trying to access a HTTP request. I'm going to generate a HTTP GET request here. I have opened a web browser here. And I'm initiating a HTTP GET request. So this part, if you see the OSI reference model, the application layer is a layer where exactly we got our payload. Our payload is the application layer. So how that sequentially happens. So we'll just look about, okay, application layer here. So I have opened a web browser and here works my layer 7. And what is the protocol I'm using here? It is HTTPS. We call this as an HTTPS TCP over TLS. So all the connections are secured. It's all encrypted. So the data is keep on encrypting for every layer. It keeps incrementing the in every layer it keeps encapsulating the data. So this is presentation layer. And you got your session and you got your transport layer. And we got the network layer here and we got the data link layer. This is layer 2 and this is layer 3. So my packet is keep on encapsulating, right? So visually how it looks, my packet is something like, see, from here, this is layer 7. And what is the payload? That is HTTPS. And it will be sent to the layer 6 presentation layer. All this data formats will be happening here. And then it comes to transport layer. The key things we are looking here. So inside the transport layer, so it's going to decide I'm going to use TCP or UDP. So I'm going to use TCP here. Right? Inside the TCP, you got multiple flag values. We'll discuss about that, but an overview inside the TCP. Okay, so I'm using TLS. Then in the network layer, it's going to specify the source IP and destination IP details. And finally, the layer 2, it has source MAC, destination MAC, and all this package is in a one single package. And if you look at, if you tear down this TCP packet here, actually your payload will be encapsulated, right? So my actual payload of this is an web traffic. This particular payload, it's keep appended until it reaches a TCP, and from the TCP it will check is it a TCP or UDP, and along with the payload, and it will send to the IP layer, then layer 2. So this encapsulation keep happening until it reaches a layer 2 from PC. So all signals, it doesn't understand about anything. So whole thing is a package. So it's going to push this packet back to the destination. And this is, I call this as a top-down approach from the sender, and it is a bottom-to-top approach. So it keep decapsulating, right? So my router is only interested in the IP packets. I'm not interested in layer 2. So in the same way, switches, it will just look for the MAC address. And if it needed, it will do all this, the router, it will do, okay, so this particular IP is in my network, but I don't know the MAC address. So here comes an R. So this packet is keep on encapsulated until this TCP, and it will open up, and it would see, right? And this is a peer-to-peer connection. It's an end-to-end connection. So this is about an overview of how these packets are encapsulated and decapsulated. When it comes to specific about TCP connection establishment, it comes to TCP connection establishment, this is my source and this is my destination. So I have encapsulated all the packets now. Now what happens? It will send a SYN packet. That is something like, hey, I want to establish a connection with you. Can you respond me back? But here comes the question. So inside the TCP sync, what are the information it would send? That is important, right? Okay, let's see. Now, I said this is a 3-tuple connection, and I have sent a SYN. For this SYN, it's going to say SYN ACK. For your SYN, I'm acknowledged. I'm okay to establish a connection now. For your SYN, I send a SYN ACK. So that's kind of an agreement. Okay, I am also okay to receive your traffic. So for this SYN ACK, it's going to send an ACK. And here the connection established. Until this point, no application data, no payload. So here we say it is in a ghost bytes. The sequence number, something like it is just for identity purpose. It just marks it as my sequence number is 1, and I'm sending this to you. If you got my SYN packet, you have to acknowledge this back. So it's going to say, okay, I received your packet, so I'm going to acknowledge, and my acknowledge bit is set, and it's going to send this back. So inside this TCP, if we peel out the TCP packets and parameters, so you can see what is SYN flag. If it is a SYN flag set, then it is a SYN packet. If it is a reset packet, so it is a reset set. So reset happened here. So this is how the connection establishment happens. Then comes your actual payload. So now let's see how we can see all this information with a complete visual in Wireshark.